Okay, so in the previous video, we have seen how you can specifically estimate the value of alpha and beta. Okay, so we saw that to do so, we need to minimize the sum of the squared residual, the errors. So here I have three estimated regression models. So what we're going to do is to interpret the coefficient estimates, so specifically the value of alpha and beta in each of the regressions. Okay, so let's start with the first one. So one thing you need to keep in mind is you always have to observe the unit of measurement for each variable in your interpretation. Okay, you have to include the units of measurement. So for instance, say income is measured, let's say in dollars, and age is measured in the number of years, right? So the intercept here would mean that individuals with zero age earn an average income of negative $0.4. Okay, in this case, that estimate is something that is sensible. Okay, because you don't really expect a newborn, so someone whose age is 0, to be earning a positive wage. Then for the slope, it will mean that if age increases by 1 year, okay, so the income is going to go up by $2.7. Okay, why did I say go up? Because the coefficient is positive, right? So if age increases by 1 year, then the income is going to go up by $2.7. Then for the second one, this is a regression of hourly earning on the years of education. Okay, you see that this time the intercept is a positive number. So it means that individuals with 0 years of education earn an average hourly wage of $2.7. Okay, now that is something that makes sense, right? Because you can see someone without any education, but they're still going to be working and earning something, right? So the only thing is that when you compare what they're earning with someone that has education, then there will be a significant difference, right? Then the slope here is 4.8, meaning that an increase in the years of education by 1 year, okay, raises the hourly earning by $4.8. So again, I said raises because the coefficient is positive. And then in the last one, we regress the health score on age. Okay, we regress the health score on age. So the intercept is 0.4, so meaning that individuals with 0 age have an average health score of 0.4. Okay, but if age goes up by 1 year, the health score drops by 0.8. Okay, depending on whatever is the unit of measurement for the health score. Okay, but you can see that that is something that makes sense, because as you're getting more advanced in age, okay, your body is becoming susceptible to different health problems. Okay, so it really makes sense that an increase in age is associated with reduction in health. All right, so yeah, okay. Now I'm going to point out one. So just like I told us, in the case of simple linear regression, where you have just one independent variable, so the error term, the error will always be large. It's as simple as that, okay? Because there are so many other factors that affect the independent variables: income, hourly earnings, health score, which we didn't add to the model, okay? So take for instance, in the first model, I mean, years of education is not there, right? And experience is not there, IQ is not there, gender is not there, and these are factors that affect income, okay? And the same thing also applies to hourly earnings. So age isn't there, okay? IQ, gender, and so many other factors. And then for health score, I mean, the only thing we control here is just the age. So is that the only thing that affects the health? No. income is a major factor. So if you're rich, then you're able to afford hospital treatments, and that will improve your health score. But income is not included here. So you see that there will be major errors going on in these estimated models. Okay. So that's why whenever you're estimating a simple linear regression, your estimate will always be, wrong. It wouldn't be accurate in most cases. Then another issue here is we're basically assuming that the impact of age on income is linear. Okay, so there is also a misspecification problem going on here. We're assuming that the impact of age on income is linear, but that is not the case. Okay, so what this assumption means, what we have here means that so far your age continues to go up, your income will continue to increase. Okay, but that is not the case, because at some point you're going to get towards a retirement, right? You're going to get towards retirement, and immediately that retirement is attained, what happens to the income? So it could start to drop. So you see that what should capture the effect of age and income should be a nonlinear model. Okay, it should be nonlinear in the sense that we're going to regress income, okay, on alpha plus beta 1 age plus beta 2 age to the power of 2, okay, age to the power of 2. So that when you plot things out, so if you plot out the relationship, you're going to have something like this. Okay, so meaning that initially, as your age is going up, your income is going to be going up. But at some point, a maximum age is attained. And after that, what happens? I mean, a maximum income is attained. And after that, it starts to drop. Okay, so that maximum could be, once you hit your retirement, right? Then after that, your earnings will start to decline. So the nonlinear model would be what will capture the impact of age on earnings more accurately. But anyway, we're still going to get to that, because you see that if we're adding something else, then we're basically moving away from the simple regression model that has one independent and one dependent variable. Okay, so it's as if we're now moving into the multiple regression analysis, but we're still going to get there. Now another thing we're going to do is we're going to see how changing the values, the individual observations of the dependent and independent variable is going to affect the value of the slope and the intercept. All right. So what do I mean? So let's say we're still working with income. Okay. So now to simplify things, to give us something we can easily work with, I'm going to replace the dependent variable with, let's say, the y, okay? And the independent variable with x. So we're going to have y equals alpha plus beta x plus the error. So the first thing we're going to try is, what if we decide to raise the individual values, okay, the individual values of y, okay, by multiplying each of them by a fixed number, say 5, all right? So if we do that, then the new y is going to be 5 times the old one, and we're regressing it on alpha plus beta x plus the error, okay? So how can you know how such a multiplication is going to affect the value of x, the value of alpha and beta? So you directly need to go back to the formula, okay? You need to go back to the formula. For instance, we know that beta is the covariance of x with the y divided by the variance of the x, okay? So that's what we have to do. So it becomes the covariance of x with, and the new value of y becomes 5 times y. Okay, 5y over the variance of x, right? So immediately we see that we can, factor the 5 out, so it becomes 5 covariance of x with y, and divided by the variance of x. Okay, now just this part alone is the original formula for beta. Okay, so that means we're going to have 5 times the beta. So you see that if you multiply the value of the dependent variable by a fixed number, okay, then it's going to raise the value of the beta by that that fixed number. So for instance, 5 times the beta. Okay. All right. Now the next one we're going to do is we're going to do the opposites. Okay. So let's do the opposites. So we're going to say y divided by, say, 5 equals alpha plus beta h plus the error. Okay? What does that mean? So we still go back to the formula. Beta is the covariance of x with y divided by the variance of x. So covariance of x with. Now the new y becomes 5 over y over 5, right? Divided by the variance of x. So if we factor out, we're going to have the 1 over 5 outside. Then the covariance of x with y divided by the variance of x. Okay? Now this part again still gives us the original value of beta. So that means we're going to have 1 over 5 times the original beta, which is beta divided by 5. Okay? So which means if you divide each observation of the dependent variable by a fixed number, then the original beta is going to get divided by the same fixed number to get the new value of the beta. Okay? So in this way, you don't really need to start trying to estimate a new model. You can just do a manipulation like this, and you can already say that this is going to happen to the new beta we're going to have. Okay? Then the next thing we're going to do now is let's apply the same thing to the independent variable, the x. Okay? So say y equals alpha plus beta 5x, okay, plus the error. So again, the beta, okay, is going to be the covariance of the new 5x with the y divided by the variance of the new 5x. Okay? So what would that be? In fact, we bring out a 5. So 5 covariance of x with y divided by. Are we done? No. What are the variance of this? So it's going to be 25 times the variance of x. Okay? So whenever you are taking the variance, the coefficient gets squared. So again, this is by default the beta, right? Good. And then we're going to cancel out. We'll have 5 there. So it's going to be basically the original beta. Okay, the original beta that we have. We're going to divide it by, say, 5. So you see that it creates an opposite impact. It creates an opposite effect here, right? All right, so that's that. Then another thing we're going to do now is I mean, the other way around. So let's say we have y equals alpha plus a beta. So x divided by 5, all right, plus the error. So we're going to do the same thing now. So we're going to have a covariance of x over 5 with the variance of with y, okay, divided by variance of x over 5. Okay. So what is that going to be? Well, we factor out the 1 over 5. We have 1 over 5 a covariance of x with y, right? And everything divided by, we square, right? So it becomes 1 over 25 and multiply the variance of x, okay? 1 over 25 multiply the variance of x, right? So of course we know that this part is already the beta itself. Then the 1 over 5, okay, times the 25 over 1. So everything is just going to give us 5. So in the end, we're going to have 5 times the beta. Okay, so you see that it creates opposite effect. So for the dependent variable, if you multiply all the observations by 5, then what happens to the beta? The new beta becomes 5 times the old one. Again, if you divide each observations of the dependent variable by 5, then the old beta gets divided by the same 5 to get the new one. But for the independent variable, if you multiply each observation by 5, then the new beta is going to be the old beta divided by 5. And if you divide the independent variable by 5, then the new beta is going to be the old beta multiplied by 5. Okay, so, but you see that if we start to do something outside this, then it becomes very problematic to do. So for instance, let's say we want to subtract, okay, a fixed value from all the x's and all the y's. So that is where you really need to actually calculate things and to know what is happening, because it wouldn't be very easy to apply what we did here to such a case. Okay. So what I'm saying is, if we decide to say y minus a fixed value, let's say 5, or y plus 5, okay, and then x minus a 5 and x plus 5, and then we want to see how that is going to affect the beta. So that is the case where you really need to follow the process and estimate a new beta to see the impact. Okay, so what we have here wouldn't really be that easy to apply in that situation. So unless you're going to follow the error minimization process to calculate the value of the new alpha and beta. So of course, everything we've done here is for the beta. So can we also do it for the alpha? Of course we can, right? So we can also do that for the alpha. So the one thing you always have to keep in mind is you have to start from the value of alpha, right? So the alpha is going to be the y bar, okay? Then minus the beta x bar. Okay, so the y bar minus the beta x bar. So you can just plug in the new value you have for the y, and then how it also affects the beta. And then from there, you're able to say what is going to happen to the alpha. But in regression, what is particularly important to us is always the slope. Okay, so that is what we particularly care about, okay? Because it is very important for policy purpose, right? It's very important for policy making. So what do I mean by that? Well, you can consider the situation like this. Say, so it is generally known that when the government intervenes, okay, so it is generally known that it is possible for the government to intervene and introduce, maybe to raise the minimum wage, okay. Of course, the The reason for doing that is to help the employees, the workers, so that they're able to earn more income. Okay, now that is a good intention on the part of the government, but it can create unintended consequences. All right. So say we go directly to the labor market. So here is going to be the wage, and this becomes employment. Okay, the supply for labor, the demand for labor. Okay, so at this point we have the wage rate equilibrium. Okay, so if the government intervenes, if the government feels that this equilibrium wage rate is not enough, okay, it's not enough, that they want to raise it, then we can just push it up to a W1. But you can see what is going to happen. So that high wage is going to cut down the demand for labor, okay? But since it's high enough, so many workers are going to supply their labor, okay? So the difference becomes the so-called structural unemployment, okay? So the difference becomes the structural unemployment in the economy. So that means we can decide to regress the unemployment, okay, on alpha plus a beta minimum wage, okay. So we can decide to regress unemployment on minimum wage. Okay, so why would we want to do that? Because of course we know that doing so is going to generate more unemployment. Okay, but if the government really wants to control, how serious that unemployment is going to be, then you see that predictions becomes necessary here. All right. So for instance, suppose we estimate this model, and we have something like this. So I'm just giving these numbers from my head, okay? Plus 2 wage, okay? So this means that if the wage goes up by, say, $1, if the minimum wage goes up by $1, then the unemployment rate is going to go up by, say, 2%, okay? So we can predict things. So the government could say, if we raise the wage by a specific amount, okay, what is the impact it's going to have on the unemployment? Okay, so for instance, what if we just fix a new wage? What if we raise it by just 1? Okay, we raise it by 2, 3, 4, 5, 6. Okay, so if we choose these values of wage, what is the impact on unemployment? So it's just about predictions. You take the new value of wage, you put it there, it becomes 2 times 1, 2, plus 10. The new unemployment becomes 12. Well, if the new wage is going to be 2, plug it in, 2 times 2, 4, plus 10, it becomes 14. Okay, so if it's going to be 6, then 2 times 6, okay, it becomes 12. You add the 10 to it, it becomes 22. Okay, so you see that it's very easy to make predictions with such things. You can also decide to predict backwards. Okay, so for instance, if I want the unemployment level to be as low as 2%, okay, then where should I set the wage? So how can you do that? So you just put the 2 there. You have every other thing except the wage. So you solve and find the value of wage. Okay, so what I'm just trying to make you understand is that the point of the regression is just we really need to know the value of the beta because it is important for policy making. All right. Yeah, so I do hope we've learned something important, just from what we've done today.